Decision-making is a process. It's really a manufacturing process. You have raw materials, which is your data. You have machinery, which represents your models and algorithms. And you have a finished product, which is the choice itself. So today is all about the architecture of choice.
The architecture of choice. I really love that phrase. It implies that we can actually design better choices if we just build the right building blocks. And the mission for this deep dive, for you listening, is to unpack exactly how that happens. We're going to look at how we build systems that help humans process information when the world is just moving way too fast for the naked brain to keep up.
And we're going to get technical. For the engineers listening, we're going to look at the specific architectural components that make this work. We really need to talk about the tension between human intuition, which is fast but super buggy, and machine logic, which is precise but very rigid. We're talking about decision support systems, or DSS, and business intelligence, or BI.
So let's start by defining the beast here. You mentioned DSS. How is that actually different from literally any other software a company uses? I mean, my payroll software makes decisions, doesn't it? It decides how much tax to deduct. The checkout scanner at the grocery store decides how much to charge me for a gallon of milk. Why do we need a whole special category for this?
That is the fundamental distinction we have to make before we go any further into the weeds. In the engineering of information systems, we view this as a continuum. It's a spectrum of intelligence. You really can't just lump all software together into one bucket.
Okay, walk us through the spectrum. Where do we start?
At the very bottom, the absolute foundational layer, you have what we call transaction processing systems, or TPS.
TPS. Okay, got it.
Yeah. Think of a TPS as the muscle memory of an organization. It is purely reactive. It records routine, highly structured events. You go to a grocery store, you scan a barcode, the system goes beep. The inventory count for milk goes down by 1. The cash drawer log goes up by $4.
It's just a digital diary, basically.
Exactly. It's strictly recording the past. There is zero ambiguity. The price is the price. And it's vital. Obviously, if your TPS breaks, you can't take money. You go out of business. But it is not intelligent in a strategic sense. It's just keeping the lights on. It handles the now of the transaction, but it doesn't care about the why or the what next.
Okay, so that's the basement level. Essential, but very basic. What's the next floor up from the basement?
Moving up, you have management information systems, or MIS.
Yeah.
These are essentially your reporting tools. They sit on top of the transaction data, and they aggregate it. So instead of just one milk sold, the MIS gives you a report at the end of the month saying, we sold 5,000 gallons of milk in February.
Useful, but you're still just looking in the rearview mirror.
Correct. It tells you what happened. It summarizes the past. It answers the question, how did we do? But it doesn't tell you why you did that well, and it certainly doesn't tell you what to do next to do better. And that is exactly where the decision support system, the DSS, comes in.
So the DSS is future-focused.
It is entirely focused on the future, and even more importantly, it is focused on what engineers call semi-structured problems. This is a massive key term in the literature. A structured problem is, how much tax is 10% of $100? There's one right answer. It's a calculation.
Right, you don't need to form a committee to figure that out.
But a semi-structured problem is totally different. It's questions like, should we expand into the Asian market next year? Or, how should we price this airline ticket right now to maximize revenue? Or even, which marketing campaign will yield the highest ROI?
There isn't a single correct answer to those.
No, absolutely not. There are only better or worse choices, depending on 1,000 shifting variables. And you can't calculate it with a simple formula. You need what-if scenarios. You need to model different outcomes. You need to weigh risks. That is the domain of the DSS.
No, the DSS isn't there to just give you the answer on a silver platter. It's not a magic oracle that says, hey, do this.
Precisely. The definition we use in the field is that a DSS couples the intellectual resources of the individual with the capabilities of the computer. It's a partnership. The computer has the speed, the memory, and the massive calculation power. The human has the intuition, the real-world experience, and the context. The DSS is the bridge that connects them to improve the overall quality of the decision.
Okay, so if we are going to engineer one of these systems, if we actually want to build this bridge, we need to know what it is made of. It's not just a black box. In the literature we pulled, they break it down into a specific architecture with 3 distinct pillars.
That's right. Every true decision support system stands on 3 legs. You need the data component, the model component, and the user interface. If any one of those is weak, the whole system just collapses on itself.
Let's unpack the first one then, the data component. This seems like the most obvious one, right? You can't make decisions without data. But the sources emphasize a really specific engineering challenge here. They say you can't just plug a DSS into your standard day-to-day database. Why not? I mean, data is data, isn't it? If I have the sales numbers in my PPS, why can't I just analyze them right there?
You would think so, but from a purely engineering standpoint, they are two completely different animals. If you plug your heavy analytics engine directly into your operational database, the one handling the checkout scanners, you are going to crash your business.
That sounds a bit dramatic. Why exactly?
It comes down to how the databases are fundamentally built. Operational databases are designed for transaction processing. They are optimized to be incredibly fast at updating a single record, like update inventory -1. To achieve that lightning speed, they are normalized.
Normalized. Define that for us in this context.
Normalization is a database design technique where you chop the data up into thousands of tiny separate tables to avoid any redundancy. So you never store the customer's address twice. You store it once in an address table, and then you just link to it everywhere else.
So the customer's name is in one table, their address is in another, their order history is in a third, the product details are in a fourth.
Exactly. It is highly efficient for cheap storage and super quick single updates. But to analyze that, to ask a broad question like, show me a 5-year trend of customers in Ohio who bought milk forming, the computer has to join all those tables back together. It has to glue the name to the address to the order to the product.
And that takes a lot of processing power.
A massive amount. If you run that complex query while the store is open, the database just locks up. The checkout scanners freeze because the database is too busy thinking about your 5-year report. You literally stop commerce.
Okay, I see the problem. You can't have the analysis slowing down the actual money-making part of the business.
Plus, operational data is volatile. It changes every single second. If you run a report at 9 a.m. and I run it at 9:05 a.m., we get different numbers because sales happened in those 5 minutes.
Right.
You can't make strategic long-term decisions on shifting sand. You need a stable foundation.
So the solution is what? We build a separate bunker just for the data.
Effectively, yes. This is the whole concept of the data warehouse. A data warehouse is defined by 4 core characteristics. It is subject-oriented, integrated, time-variant, and non-volatile.
Time-variant and non-volatile, those sound like physics terms.
They essentially mean that once data goes into the warehouse, it never, ever changes. It becomes a permanent historical record. We take the data out of the operational system, we clean it up, we stamp it with a date like this is the state of the world on February 25th, and we lock it down. It's non-volatile. It doesn't evaporate or change when a new sale happens.
So Bolichian analyzed it without slowing down the cash registers, and we know the numbers won't constantly change under our feet while we're trying to do the math.
Exactly. But simply storing it isn't enough for a DSS. We have to structure it for speed. The sources talk about a concept here called the cube, or technically, MLOLAP, multidimensional online analytical processing.
MOLAP, that sounds like a 1950s sci-fi villain. I'm MOLAP, destroyer of spreadsheets.
It's actually the hero of the story. Imagine a standard spreadsheet. That's 2 dimensions, right? Rows and columns. Maybe you have products on the left and months across the top. You can easily see how many widgets you sold in January.
Simple enough.
But real business questions are rarely that simple. The CEO doesn't just want to know about widgets in January. They want to know how many widgets did we sell in January in the North region. Now you need a 3rd dimension. You need depth.
Okay, so a 3D cube, I can picture that.
Keep going, though. How many widgets in January in the North region sold by salesperson Steve to corporate clients? Now you have 5 dimensions.
My brain is hurting just trying to visualize a 5-dimensional spreadsheet.
And that is exactly the point. A standard relational database chokes on that. It has to do all those table joins we talked about earlier. But in a data cube, we pre-calculate all those intersections. We build the hypercube in memory overnight. This allows the user to slice and dice the data instantly. You can take the cube and slice it to just look at Steve, or rotate it to look at the North region.
And because it's already pre-calculated, it's instant.
Instant. You aren't waiting for the computer to do the math. The math is already done. You are just navigating the architecture. That is the true power of the data component. It turns a query that might take 6 hours on a normal database into one that takes milliseconds.
But before we even get the data into the cube, we have to talk about data scrubbing. The sources bring up a really specific, really tricky engineering problem regarding currency. I thought this was fascinating because it shows just how messy real-world data actually is.
Oh, the currency problem is the classic example of dirty data. It literally keeps data engineers up at night.
Walk us through it. Why is it so hard?
Let's say you are a global company. You have a warehouse in Germany. 6 months ago, you bought inventory, let's say 10,000 microchips for 500,000 euros. At that specific time, The exchange rate was maybe €1 equals 1.10 US dollars.
Okay, so on the books, that translates to $550,000.
Right. Now, fast forward to today. You still have those chips sitting on a shelf. You want to run a report on your current inventory value. But today, the exchange rate has shifted. Maybe the euro is weaker. If you just take that 500,000 euros and convert it using today's rate, the value in dollars will look much, much lower.
So it looks like you lost a bunch of money.
Exactly, but you didn't actually lose money on the chips themselves. The chips are perfectly fine. The discrepancy is purely a phantom shift caused by the currency market. If your decision support system doesn't account for that, it is flat out lying to you. It's telling you that your inventory management is terrible when actually it's just the Forex market moving.
So the data warehouse has to be smart enough to remember what the exchange rate was on the specific day of the original transaction.
Yes, you have to scrub and adjust the data as it goes into the warehouse to ensure comparability. You have to lock in that historical rate. Otherwise, you are making major strategic decisions based on noise, not signal. That is what we mean by the data component being a serious engineering challenge. It's not just copying files over, it's reconstructing reality so it actually makes mathematical sense.
Which naturally leads to the issue of granularity. The sources talk about the constant trade-off between detail and summary.
It is the ultimate engineer's dilemma. You want the most detailed data possible, right? Every single click, every single keystroke. That is high granularity. It allows for the deepest possible analysis. You can ask, why did this specific customer leave the website after exactly 3.2 seconds?
But storing every single click for millions of users requires massive storage.
Massive storage and very, very slow processing. It's like trying to find a needle in a haystack the size of Montana. On the other hand, if you summarize the data, say, you just give me daily total sales, it is super fast and very cheap to store. But you lose the ability to ask why.
You can see that sales dropped on Tuesday, but not why they dropped.
Correct. So a good DSS architecture usually tries to offer a hybrid approach. You have highly summarized cubes for speed, so the CEO can get their morning dashboard instantly, but with a drill-down capability that reaches back into the massive archive to get the raw, granular data when you spot a red flag or an anomaly.
Okay, so we have built our foundation. We have clean, historical, multidimensional data. Pillar 1 is complete. Now we need the engine. Pillar 2, the model component.
Right, because data is really just numbers. It's static. A pile of bricks isn't a house. You need a blueprint. In a DSS, the model is the blueprint. It is a mathematical simplification of reality that helps us understand behavior.
The outline lists a few main types of models: statistical, optimization, and simulation. Let's break those down.
Statistical is your bread and butter. It's regression analysis. Show me the trend line. Based on the last 5 years of sales, predict the sales for next year. It inherently assumes the future will look somewhat like the past.
But optimization sounds a lot more active.
Optimization is where it gets really cool for engineers. This is all about finding the mathematically best possible solution, given a strict set of constraints.
There was a great example in the reading about the diet problem. This dates back to the mid-20th century, right?
Yes, this is a classic operations research problem from the U.S. Army. The goal was simple on paper. We need to feed our soldiers. We have a list of available foods: beef, potatoes, spinach, milk, whatever. We know the exact cost of each item. And we know the exact nutritional content, like calories, protein, vitamins.
And the constraints.
The constraints are biological. The soldier absolutely must get at least 2,000 calories, at least 50 grams of protein, a certain amount of iron, etc. The mathematical problem is, what is the exact combination of foods that meets all those nutritional requirements for the lowest possible financial cost?
It sounds like a pretty simple math problem when you just say it out loud.
It sounds simple, but the number of permutations is in the millions. What if I add a little more beef and slightly less potato? What if I swap milk for cheese? In the early days, solving this by hand using a method called the simplex algorithm took a room full of 9 clerks, about 120 days of nonstop calculation.
120 days. By the time they figure out what to serve for lunch, the war is already over.
Exactly. Fast forward to today. The model component in a modern DSS uses linear programming to solve that exact same problem in a fraction of a second. It literally churns through every possible combination of food and cost and spits out. The optimal solution is X amount of beef, Y amount of potatoes. It's a guess. It mathematically knows the optimal path.
That is incredible. And then there's the third type, simulation. This is the what-if engine.
Right. Optimization tells you the absolute best thing to do right now. Simulation tells you what might happen in the future if the world changes unexpectedly. What if interest rates go up by 2% next week? What if our main supplier in Taiwan goes bankrupt?
because you can't actually bankrupt your supplier just to see what happens to your revenue.
That would be highly frowned upon. So you simulate it mathematically. You create a digital twin of your supply chain, and you intentionally break it in the computer. This allows you to stress test your decisions before you commit real money to them.
The text mentions something called an MBMS here, a model-based management system. Is that just like the folder on the desktop where you keep the files?
Think of it more like an intelligent library for your algorithms. You don't want to hard code one specific formula into your software. You want a vast library of formulas, linear programming, exponential sleuthing that the system can pull off the shelf dynamically, depending on the question being asked. The MBMS manages the models just like a database management system manages data. It ensures you are using the right mathematical tool for the specific job.
Okay, so pillar 1, data. Pillar 2,
Yeah.
models. Now we get to the part that I think is so often overlooked by engineers, but the research says is absolutely critical. Pillar 3, the user interface.
The research is very blunt about this. It states the interface is often the only part the user sees. If it fails, the system fails, period.
That's a really strong statement.
Yeah.
You could have the most accurate 8-terabyte data warehouse and the most sophisticated lineal programming model in the world, but if the interface is confusing,
The decision maker will just ignore it. They will close the laptop and go right back to guessing based on their gut. Engineers forget this all the time. We love the back-end complexity. We love the math. But the user isn't an engineer. The user is a stressed-out middle manager with 5 minutes to make a call.
this gets right into human-computer interaction, or HCI. And we have to talk about the cognitive limits of the human brain here, the 7 plus or minus 2 rule.
This is Miller's law. It is a fundamental biological constraint in cognitive psychology. The human working memory, your brain's RAM, can only hold about 7 chunks of information at any one time. Maybe 5 on a bad day when you're tired, maybe 9 on a good day, but it centers around 7.
So if your dashboard has 50 different raw numbers on it,
You have completely failed as a designer. You have overloaded the human buffer. The user literally cannot process it. They will stare at the screen and see absolutely nothing. A good DSS architecture must aggregate data. It has to roll those 50 numbers up into 5 key indicators. It respects the biological bottleneck of the human skull.
and then there's pre-attentive processing. I love this concept. It's all about how our eyes work faster than our brains.
Yes. Let's try a really quick mental experiment. Imagine I show you a spreadsheet with 1,000 numbers on it. They are all plain black text on a white background, and I ask you, find all the negative numbers as fast as you can.
I have to scan them one by one, read row 1, read row 2. It's going to be incredibly slow.
That is attentive processing. You are using your conscious brain. It requires active effort and time. Now imagine I take that exact same spreadsheet, but I make all the negative numbers bright, glowing red.
Boom, I see them instantly without even reading them.
Before you even consciously think, oh, that is a number with a minus sign, your visual cortex has already flagged the color red. That is pre-attentive processing. It happens in milliseconds, totally without conscious effort. A well-engineered UI leverages this biological shortcut. We use color, size, and position to push the data into your brain before you even try to read it.
It's just like the check engine light in your car. You don't have to read a complex gauge or a diagnostic code. You just see the orange light and know something is wrong.
Exactly. If a DSS engineer presents a plain table of numbers, they're making the user work way too hard. If they use a dashboard with red and green indicators, they're literally hacking the visual cortex to speed up the decision-making process.
So we have built the machine. We have the data, the models, and a UI that respects our monkey brains. But now we have to talk about the user, the human element, because frankly, humans are kind of glitchy.
We are terribly glitchy. We are not the perfectly rational machines we like to think we are.
Section 2 of our deep dive is the human element and decision theory. The text is actually titled The Problem with Humans. Why do we need these systems so badly? Why can't we just trust our gut? People have been running businesses on their gut for centuries.
Because of a concept called bounded rationality. This actually won Herbert Simon a Nobel Prize.
Yeah.
The classical economic theory used to be that humans are rational actors. We carefully weigh all the available options, and we always pick the mathematically best one.
Homo economicus, the perfectly logical human.
Right. Simon came along and said that is complete nonsense. Humans want to be rational, sure, but we are bounded. We are bounded by the limited information we have, the limited time we have to decide, and the sheer cognitive capacity of our brains. We physically cannot calculate every option.
So what do we do instead when we're faced with a big choice?
We satisfy.
Satisfy. That's a mashup of satisfy and suffice, right?
Exactly. We search for a solution until we find one that is just good enough, and then we stop looking. We don't look for the absolute best solution. We look for the first acceptable solution.
It's like looking for cereal in the grocery store aisle. There are 200 kinds of cereal. If I tried to optimize for the perfect mathematical balance of taste, cost, and nutrition, I would be standing there for 4 hours. So I just grab the Honey Nut Cheerios because I know they're okay.
That is textbook satisficing. It saves mental energy. But in business, satisficing costs a lot of money. If you just pick the good enough shipping route for your cargo fleet, you might be wasting millions of dollars in fuel a year. A DSS is designed to push us past satisficing toward optimizing. It does the heavy mathematical lifting so we can actually find the best choice, not just the first one we stumble upon.
But even if we try our hardest to optimize, we are full of biases. The sources list a few nasty ones that ruin our decisions, like the recency effect.
This is a huge one for managers. We give way too much weight to what happened yesterday, and we completely forget what happened a year ago. If sales were down yesterday, we panic. Even if the 5-year long-term trend is pointing straight up, a DSS doesn't panic. It weighs the historical data equally with the recent data. It forces perspective on us.
And what about selective perception? That one sounded really insidious.
This is often illustrated with the old woman versus young woman optical illusion. You know the one I'm talking about.
Where some people look at the drawing and see a young lady looking away, and others look at the exact same lines and see an old witch looking down.
Right. And once you see the young woman, it is really hard to unsee her to find the old woman. Your brain locks onto a pattern. In business, if a manager expects a new marketing campaign to fail, they will unconsciously focus only on the data points that suggest it's failing. They will completely ignore the data that shows early success. They were selectively perceiving reality to match their internal bias.
So the DSS acts as a neutral third party in the room.
Ideally, yes.
Yeah.
It puts all the data on the screen. It forces you to look at the whole picture, not just the parts that confirm your pre-existing gut feeling.
This connects perfectly to something called the ODA loop. I've heard this a lot in military contexts, fighter pilots, and Top Gun stuff. But how does it apply to engineering a corporate decision system?
ODIA stands for Observe, Orient, Decide, Act. It was developed by Colonel John Boyd. He analyzed air combat in the Korean War. He found that the pilot who could cycle through this mental loop the fastest thing has been observe the enemy, orient themselves to the situation, decide on a move, and act that pilot would win the dogfight.
Speed is the weapon.
Speed is life. If I can go through the loop in 5 seconds and it takes you 10 seconds, by the time you finally act, I'm already doing something else. Your decision is obsolete before you even make it.
So in the business context, this is what the reading calls vigilant information systems.
Exactly. Business is a dogfight. Competitors, global markets, shifting customer trends, they are all fast-moving targets. The fundamental problem is the tension between speed and smarts. Usually if you go fast, you make stupid mistakes. But if you stop to do deep analytics, you go too slow and miss the window.
The classic analysis paralysis.
Right. So the DSS bridges that gap. The goal is to fully automate the observe and orient phases of the loop. The computer collects the raw data to observe and analyzes it to orient instantly. That frees up the human brain to focus entirely on decide and act.
It accelerates the loop without sacrificing the intelligence behind it.
That is the holy grail of system design. Speed and accuracy simultaneously.
Let's look at a real-world example of this, because the theory is great, but I want to see it actually working. We have a massive case study here on Continental Airlines.
This is truly legendary in the BI world. In the late 90s, Continental was in really bad shape. They were practically bankrupt. They decided to basically bet the farm on real-time business intelligence.
And when you say real-time, you mean truly real-time, not batches.
Yes, not monthly reports. They built an 8-terabyte data warehouse that was updated second by second with live operational data.
And they used it for something called demand-driven dispatch. Explain how that works for an airline.
So the old way of running an airline was highly rigid. You set the flight schedule months in advance. Flight 101 from Newark to LA is a Boeing 737. Flight 102 to Cleveland is a smaller regional jet. That is the schedule. It's printed on paper. It's done.
Even if suddenly everyone wants to go to Cleveland.
The old system couldn't handle that. You would just turn people away because the small plane was full. But with the real-time DSS, Continental could see bookings happening live. If they saw that the flight to Cleveland was selling out like crazy, maybe there is a big sports game or a sudden convention, and the LA flight was practically empty.
The system flags the anomaly.
The system says, swap the planes right now, put the big 737 on the Cleveland route, and the small jet on the LA route.
Wait, can you just do that? Swap commercial planes around.
If you catch it early enough in the cycle, yes. And the financial result was massive. It's just that one application generated $5 million a year in incremental revenue because they weren't turning away paying passengers on the full flight, and they weren't flying empty seats across the country on the other.
That is pure operational efficiency. And then there is fair design.
This is dynamic pricing. We usually hate it as customers, but as engineers, it's a beautiful piece of logic. The system constantly watches booking velocity. If tickets for a specific flight are selling faster than normal, the algorithm automatically raises the price. If they're selling too slow, it slightly drops the price to stimulate demand. It's real-time, continuous optimization. That tweak alone was another $10 million a year.
But my absolute favorite part of this case study is the customer service angle, because we usually think of these massive data systems as cold and corporate, just squeezing every last dime out of people. But here they used it to actually help people on a personal level.
This is the gate agent example.
No.
It perfectly illustrates the power of empowering the frontline worker with processed intelligence.
Paint the scene for us.
Imagine you are a gate agent at a massive hub like Houston. It's a busy day. You have a flight closing its doors in 10 minutes. You see a passenger running down the concourse toward the gate, but they are late. In the old system, you just see a name on a green terminal screen. Can't just close the door because your boss wants an on-time departure metric.
You don't know their story or how important they are.
But in the new Continental system, the agent saw a special icon, a dash or a star right next to the name. That little icon meant high-value customer and connecting flight at risk.
The system has already connected all the dots in the background.
It has observed and oriented in a split second.
Yeah.
It tells the agent, this guy flies with us every single week. He's a VIP, and the only reason he is late is because his incoming flight was delayed by weather. It's our fault.
So the agent has the exact context needed to make a much better human decision.
Right. The agent can decide, I am holding this plane for 5 extra minutes. It is worth the slight delay penalty to save this million-mile customer relationship. Or, if it's truly too late to hold the plane, the system might have already rebooked him on the next flight out and automatically booked him a hotel room before he even arrives panting at the gate.
Imagine the difference in that customer experience. Instead of a stressed agent saying, sorry, you missed your flight, it's, Mr. Smith, I see you're delayed. Don't worry, we already have your new boarding pass ready and a hotel voucher waiting for you.
That turns a complete disaster into fierce brand loyalty. And it's all because of back-end data architecture. The data warehouse isn't just some dusty archive in the basement anymore. It is driving the actual business operations second by second. It totally blurs the line between decision support and operational execution.
Okay, so Continental clearly shows us the incredible power of giving people the right information at the right time. But there is a darker or maybe just more philosophical side to system design. When we design these systems, how much control do we actually give the user?
This brings us to the concept of restrictiveness versus decisional guidance. It comes from the research of Mark Silver. It's a really fascinating ethical and design question for engineers. Do we actually trust the user to make the right call?
Let's start with restrictiveness. This sounds like putting heavy guardrails on the system.
It is exactly that. Restrictiveness is strictly limiting what a user can do within the software.
But why would you want to do that? I thought the whole goal was human empowerment.
Well, remember bounded rationality. Remember all those biases we just talked about?
Yeah.
Sometimes users have gut feelings that are demonstrably mathematically wrong, or they just make simple, stupid errors.
So like preventing someone from accidentally entering a negative number for a person's age?
That's a simple technical restriction, sure. But it can be much deeper than that. It can be prescription. The system might deliberately prevent a marketing manager from using a forecasting method that is known to be statistically invalid for the type of data they are looking at.
So if I try to use a linear projection on highly seasonal data, the system literally says, no, stop. That's bad math.
Exactly. It saves the user from themselves. It enforces organizational consistency. But if you make a system too restrictive, users get incredibly frustrated. They feel like the machine is bossing them around, and they might just abandon the system entirely.
So you have to carefully balance it with decisional guidance.
Right. Guidance isn't physically stopping you. It's nudging you in the right direction. It's enlightening you.
Nudging is such a powerful concept in behavioral economics. How does the software system nudge?
Well, there is inadvertent guidance. This happens completely by accident. If you present a drop-down menu of 5 options, statistically, people tend to pick the very first one on the list much more often. That's called the primacy effect.
So if I list high-risk investment as the first option on a banking screen, I am accidentally encouraging my employees to take massive risks.
Yes. An engineer needs to be hyper-aware of that. You might be completely biasing the human decision just by how you sort the list alphabetically. You are architecting the choice without even realizing you're doing it.
And what about active guidance?
That's highly deliberate. That's the system saying, hey, I notice you're looking at historical sales data right now. Based on this pattern, I strongly suggest you also look at the competitor price report before you make a move. It's like an intelligent suggestion box. Or it could be a warning light. Warning. Your growth assumptions seem wildly optimistic based on current market trends.
This leads perfectly into our next major case study, which is all about how UI design and this concept of guidance changed an entire justice system. This is the Manhattan court system case.
This is a really profound example because the stakes are so incredibly high. We aren't talking about airline tickets or widgets anymore. We are talking about human liberty, jail time versus rehabilitation.
So set the stage for us. What was the core problem in Manhattan?
The environment was extremely high volume, quality of life crimes, shoplifting, turnstile jumping, petty theft, things like that. The judges were completely overwhelmed. They were seeing dozens and dozens of cases a single day.
The whole assembly line of justice concept.
Right. And the judges suffered from a severe, crippling lack of information. They had physical paper files, but they were messy, totally incomplete, and sometimes 3 inches thick. They couldn't quickly find what they actually needed.
The source material says 40% of these defendants had 3 or more prior convictions. It was just a massive revolving door.
It was a revolving door, and because the judges couldn't see the whole picture, like, was this guy stealing bread because he's homeless? Is he a severe drug addict? Is he a professional career criminal? They tended to just default to a standard easy sentence, time served or standard community service. They were satisficing. They were doing what was easiest because they simply didn't have the process data to do what was best for society.
So the city decided to build a DSS, but they didn't focus on complex predictive algorithms. They focused entirely on the interface.
They realized the actual bottleneck was the judge's cognitive attention. So they got rid of the thick paper file. They replaced it with a single computer screen divided neatly into 4 quadrants.
Paint the picture for us. What did the judge actually see on the monitor?
Quadrant 1 was the current incident. What do they do today? Quadrant 2 was criminal history, the rap sheet. Quadrant 3 was lifestyle and social data. This was the absolute game changer. It showed housing status, drug use history, employment records. In Quadrant 4 was the decision or sentence options.
That third quadrant lifestyle seems very new. Usually, courts just look at the crime in a vacuum.
It was crucial. And here's exactly where the decisional guidance comes in. The system used brilliant visual cues. If a defendant had a documented history of drug use, that specific item will be highlighted in bright red text.
Pre-attentive processing strikes again.
Exactly. The judge doesn't have to speed read 50 pages of legal jargon to find out there's a drug problem. The red text jumps right off the screen at them. It practically screams, this is a root cause.
And they could drill down if they needed to. Yeah.
Yes. If the judge wants context, they click the red text and they see the deep details. But the top-level summarized view forces the judge to see the behavioral pattern immediately.
So the big question, did it work? Did better data presentation actually lead to better justice?
The real-world outcomes were staggering. Before the new system, only 40% of these offenders ever completed their community service sentences. It was a massive failure. After the system was implemented and the judges started using it, the completion rate jumped to 80%.
That is a massive jump. It doubled. Why did it work so well?
Because the system made the background information instantly actionable. It allowed the judges to quickly fit the sentence to the actual person. They could look at the screen and say, oh, I see you have a severe drug problem. I'm not just going to fine you or put you in a cell. I'm actively sending you to a targeted drug treatment program.
So the sentence actually made logical sense for the defendant's specific situation.
Right. And this is highly key for engineers. The system tracked the outcomes over time. For the first time ever, judges could actually see if their past sentences were working. They could look at the aggregated data and say, hey, every time I send someone to program A, they get arrested again in a month. But program B actually works. It completely closed the feedback loop.
It effectively engineered a massive behavioral change in the judges themselves just by presenting data differently.
It did. It moved them from a pure processing mindset, just clear the busy docket, to a real problem-solving mindset.
Yeah.
That is the ultimate highest goal of a DSS. It's not just about speed, it's about fundamentally changing how we think and approach a problem.
That is incredibly powerful. Now, we have talked about the past and the present of these systems. Let's look forward at the future. Section 6 of our deep dive is advanced intelligence.
We have to talk about AI here.